What if everything you thought you knew about the universe was just the tip of an invisible iceberg? Picture this: the fabric of reality isn't just empty space dotted with stars and galaxies. It's humming with hidden fields, invisible forces that shape everything from the tiniest particles to the vast cosmic web. These fields aren't science fiction. They're at the heart of some of the most groundbreaking theories in physics today, and they might hold the keys to unlocking the universe's deepest secrets. Think about the last time you felt a breeze on your skin. You couldn't see the air moving, but you knew it was there. Hidden fields are like that, unseen, yet everywhere. They're the reason particles have mass, the force behind gravity's pull, and possibly even the answer to why our universe exists at all. But here's where it gets wild. Scientists still don't fully understand how these fields work. Some theories suggest they could warp space-time, create parallel dimensions, or even rewrite the laws of physics as we know them. That's exactly what we're diving into today. 30 mind-blowing theories about these hidden fields, each one more astonishing than the last. From the Higgs field, which gives particles their weight, to dark energy's mysterious push that's stretching the cosmos apart, we'll explore ideas that challenge everything we thought was possible. Some of these theories could redefine reality itself, while others might lead us to the next great leap in human understanding. So buckle up, because by the end of this journey, you'll never look at the universe the same way again. Even empty space isn't as empty as it seems. At the smallest scales, the vacuum of space crackles with energy, a seething ocean of particles popping in and out of existence so fast they defy everything we think we know about reality. This isn't just theoretical guesswork. Scientists call it quantum vacuum fluctuations, and it's one of the strangest confirmed phenomena in physics. Imagine a calm lake surface suddenly erupting with tiny bubbles, particles and antiparticles flickering into being, colliding, and vanishing again in fractions of a second. That's the hidden dance happening everywhere, even in the void between stars. But here's where it gets even wilder. These fleeting particles might be shaping the universe itself. Some theories suggest quantum fluctuations could be the engine behind cosmic expansion, the mysterious force pushing galaxies apart faster and faster. Think of it like this: if space itself is fizzing with energy, could that energy be stretching the fabric of reality? It's not just science fiction. The math suggests these tiny fluctuations might add up to something colossal, like raindrops filling an ocean over billions of years. And that's not all. There's a mind-bending idea that these quantum ripples could be the seeds of entire universes. Picture a single fluctuation growing so intense, it pinches off from our reality and blossoms into a whole new cosmos with its own laws of physics. Some physicists argue this could explain the Big Bang not as a one-time event, but as a natural consequence of these hidden fields bubbling over. It's a humbling thought that everything we see, galaxies, planets, even ourselves, might owe its existence to invisible particles flickering in the dark. So what does this mean for us? If quantum vacuum fluctuations are real, and experiments say they are, then the universe is far more dynamic, far stranger than we ever imagined. The emptiness of space isn't empty at all. It's alive with possibilities, a hidden layer of reality that might hold the answers to our biggest cosmic mysteries. This is just one thread in the tapestry of hidden fields, but already it's unraveling what we thought we knew about the nature of existence itself. Now imagine a universe where nothing has weight, where particles zip around at the speed of light, never clumping together to form atoms, stars, or even you. That's the bizarre reality we'd face without the Higgs field, an invisible ocean of energy stretching through every corner of space. Unlike gravity or magnetism, you can't feel it or measure it directly. But here's the twist: this field is why anything has substance at all. When particles move through the Higgs field, they interact with it like wading through thick syrup. Some particles, like quarks, get bogged down, acquiring what we experience as mass. Others, like photons, glide through untouched, remaining weightless. This interaction is called the Higgs mechanism, and it's the reason matter can exist in the form we know. Without it, the universe would just be a chaotic soup of particles with no structure, no chemistry, no life. But the story gets even stranger when you look at the numbers. In 2012, scientists at the Large Hadron Collider finally detected the Higgs boson, the particle that proves the field exists. Yet its mass was shockingly light, about 125 times lighter than a single proton. Here's the problem: quantum physics predicts the Higgs should be far heavier, even trillions of times heavier, based on how other particles interact with it. It's like finding a feather that somehow resists the pull of a hurricane. This mystery has led to some spine-tingling theories. Maybe the Higgs boson's lightness is a clue that we're missing something fundamental, like undiscovered particles or hidden dimensions that cancel out its expected weight. Some physicists speculate there could be multiple Higgs fields layered together, each tweaking the final number like invisible hands fine-tuning a cosmic scale. Others wonder if we're seeing evidence of a deeper principle, a symmetry in nature we haven't discovered yet. What's at stake isn't just a physics puzzle. If the Higgs field were even slightly stronger or weaker, atoms wouldn't form correctly, stars wouldn't ignite, the universe as we know it would literally fall apart. That's why understanding this hidden field isn't just academic, it's about unraveling the very blueprint of reality. And right now, its secrets are still out there, waiting to be found. Dark energy might be the most baffling force in the cosmos, an invisible push that's stretching space itself apart at an ever-increasing speed. For decades, scientists assumed it was a constant and unchanging property woven into the fabric of the universe. But what if that's not the whole story? What if dark energy isn't a steady background hum but something far more dynamic, a field that ebbs and flows, strengthening or fading over time? This idea isn't just speculation. Observations of distant supernova and galaxy clusters suggest the expansion of the universe isn't behaving as predicted. If dark energy were truly constant, the acceleration should follow a smooth, predictable curve. Instead, some measurements hint at subtle variations, like a car whose speed inexplicably fluctuates even when the gas pedal stays flat. That's where quintessence comes in, a theoretical field that could explain these quirks. Unlike a static dark energy, quintessence would interact with matter and space, its influence waxing and waning across cosmic history. Picture dark energy as a river. The constant model assumes it's a steady, unchanging current, but quintessence, that's more like a river with seasons, sometimes rushing, sometimes sluggish, reshaping the landscape as it goes. Some versions of this theory even suggest the field could eventually reverse, turning from a repulsive force into an attractive one. If that happened, the universe's expansion could slow, stop, or even collapse in a dramatic big crunch. Here's where it gets truly radical. If dark energy is a dynamic field, it might not just affect the universe's expansion, it could alter the fundamental laws of physics over time. Constants we take for granted, like the speed of light or the strength of gravity, might not be so constant after all. Imagine a cosmos where the rules subtly shift across billions of years, where the physics of the distant past or far future diverge from what we observe today. So why does this matter? If dark energy is changing, it could rewrite our cosmic destiny. A weakening field might mean the universe expands forever but at a gentler pace. A strengthening one could lead to a big rip, where galaxies, stars, and even atoms are torn apart. Or perhaps the field oscillates, driving cycles of expansion and contraction, a universe that breathes. The hunt for answers is already underway. Telescopes mapping the large-scale structure of the cosmos, experiments probing the nature of vacuum energy, even simulations of alternate physics, all are pieces of this puzzle. One thing's certain, if dark energy is a dynamic field, we're standing at the edge of a revolution in how we understand reality itself. Among the most tantalizing mysteries of the cosmos is dark matter, the invisible glue holding galaxies together, outweighing visible matter 5-1. We can't see it, can't touch it, yet its gravitational pull shapes the universe. But what if the answer lies not in some exotic particle, but in an ultra-light, nearly undetectable field permeating every inch of space? Enter axions, ghostly particles so light, they behave less like solid matter and more like ripples on an invisible cosmic pond. Axions were first dreamed up to solve a puzzle in quantum physics: why the strong nuclear force which binds atomic nuclei doesn't seem to care about the direction of time. But here's the twist: these hypothetical particles could also be the elusive dark matter we've been chasing for decades. Picture them as a vast, intangible mist filling the universe, their collective mass explaining why galaxies spin faster than they should, and why clusters of galaxies bend light like giant cosmic lenses. Unlike heavier dark matter candidates, axions wouldn't clump into dense clouds. Instead, they'd form a smooth, wave-like field, subtly tugging on stars and galaxies with an imperceptible gravitational whisper. The hunt for these phantoms is already underway. Deep underground, in labs shielded from cosmic interference, experiments like the Axion Dark Matter Experiment, ADMX for short, are listening for axion's faint signals. Think of it like tuning an ultra-sensitive radio to a channel no one's ever heard. If axions exist, they should occasionally convert into microwave photons in powerful magnetic fields. ADMX detector, chilled to near absolute zero, waits for that telltale blip, a single note in the universe's hidden symphony. But why is this search so revolutionary? If axions are real, they'd bridge two of physics' greatest puzzles, dark matter and the quirks of quantum forces, with one elegant solution. They'd also hint at something profound, that the universe might be filled with delicate, nearly weightless fields we've barely begun to sense. Some theories even suggest axions could warp space-time in strange ways, creating minuscule twists in the fabric of reality that future telescopes might spot. And the implications go deeper. If axions make up dark matter, their behavior could explain why galaxies have fuzzy edges instead of sharp boundaries. Their wave-like nature might prevent them from clumping too densely, solving mysteries about the universe's large-scale structure that heavier particles struggle with. It's like realizing the ocean isn't made of isolated droplets, but of vast, interconnected currents. Yet the axion story isn't without its skeptics. Some argue these particles are too light to account for all of dark matter's effects. Others wonder if we're chasing a cosmic mirage, projecting our hopes onto a particle that might not exist. But that's the thrill of the hunt. Each experiment, each null result sharpens the question. Whether axions are the answer or just another step toward it, one thing's clear: the universe is hiding layers of reality we're only starting to peel back. And with every passing year, our tools grow sharper, our searches more refined. The day we finally detect or rule out these ghostly particles could rewrite the story of the cosmos itself. Picture the universe in its first trillionth of a second, smaller than a single atom, yet hotter and denser than anything we can recreate. Then, in an unimaginably brief instant, it ballooned to cosmic proportions, stretching faster than light itself. This isn't fantasy, it's cosmic inflation, and the leading explanation for it revolves around something called the inflaton field. Think of it as the universe's first accelerator pedal, a hidden force that kicked expansion into overdrive and left fingerprints we can still detect today. The inflaton field isn't like gravity or electromagnetism. It's a hypothetical energy field that existed only in those earliest moments, a kind of cosmic fuel that drove space to expand exponentially. Here's how it might have worked. As the field permeated the newborn universe, it carried a strange property: negative pressure. Normally, pressure pushes outward like air in a balloon. But negative pressure does the opposite, creating a repulsive force that stretches space itself. Imagine blowing up a balloon that magically expands faster the more you inflate it. That's the inflaton field's effect on the cosmos, amplifying expansion until the field's energy finally decayed, releasing a firestorm of particles that became the first matter and radiation. But how do we know this wild idea isn't just speculation? The clues are etched into the oldest light in the universe, the cosmic microwave background. This faint glow, left over from just 380,000 years after the Big Bang, is like a baby picture of the cosmos, and it's full of tiny temperature variations, patches slightly hotter or colder than their surroundings. These imperfections are critical. Inflation predicts that quantum fluctuations in the inflaton field would have been stretched to cosmic scales, seeding the density differences that eventually grew into galaxies and galaxy clusters. Without those initial ripples, the universe would be eerily smooth, devoid of structure. Even more compelling are the anomalies we've spotted. The cosmic microwave background is almost perfectly uniform, but not quite. Some regions show unexpected patterns, large-scale cold spots, alignments of fluctuations that defy standard statistical odds. These could be scars from inflation's abrupt end, like cracks in pottery revealing how it was shaped. Some theorists suggest they hint at the inflaton field's chaotic nature, perhaps even evidence of collisions with other universes in a vast multiverse. The inflaton field's legacy isn't just ancient history. Its behavior might explain why the universe looks the way it does today, why space is flat on large scales, why matter is distributed so evenly, even why we haven't found exotic relics like magnetic monopoles. But the field raises just as many questions as it answers. What triggered its decay? Was inflation a one-time event, or does it happen endlessly, birthing new universes like bubbles in a boiling pot? Some models suggest the inflaton field could still exist in a weakened state, hiding in the vacuum of space, its residual energy fueling dark energy's push. What's certain is this: if inflation is real, it means the universe we see is just a tiny fraction of what's out there. Regions stretched beyond our cosmic horizon by faster-than-light expansion could contain entire superclusters of galaxies we'll never observe. It's a humbling thought that the inflaton field didn't just shape our reality, but potentially countless others, each with its own unique physics and history. And somewhere in the echoes of the cosmic microwave background, the answers might still be waiting. What if some hidden fields are cosmic shape-shifters, altering their behavior to stay just out of sight? That's the bizarre premise behind chameleon fields, theoretical forces that change density depending on their surroundings, like an interstellar chameleon blending into its environment. Unlike static fields, these would be elusive, tuning themselves so precisely to the local conditions that our detectors might scan right past them. And yet, they could hold the keys to some of the universe's most stubborn mysteries, from dark energy's grip on cosmic expansion to the enigma of gravity itself. Imagine dropping a marble into a pool of honey. In empty space where matter is sparse, the chameleon field would be thin and diffuse, barely noticeable. But in dense regions like Earth's atmosphere or near a galaxy cluster, it would thicken, becoming stronger and more influential. This adaptability isn't just a clever trick, it could explain why we haven't spotted these fields yet. Unlike the Higgs or electromagnetic forces, which leave clear signatures, chameleon fields would actively evade detection by weakening in the very places we're most likely to look. It's like searching for a whisper in a thunderstorm. You'd never hear it over the noise. Here's where the implications get cosmic. If these fields exist, they might be behind dark energies accelerating push on the universe. In the near vacuum of intergalactic space, a chameleon field could grow potent enough to stretch spacetime itself, mimicking the effects we attribute to dark energy. But closer to galaxies, where matter is packed tight, the field would dampen, subtly tweaking gravity's pull without disrupting the delicate balance that holds stars and planets in place. This could solve a major puzzle: why dark energy's influence seems to kick in only on the largest scales, leaving smaller structures untouched. The hunt for chameleon fields is already pushing experimental physics to its limits. Ultra-sensitive lab setups use finely tuned lasers and atomic interferometers to probe subtle forces in near-perfect vacuums and environments where these fields might finally reveal themselves. Some experiments even repurpose gravitational wave detectors, hunting for faint ripples that could betray a chameleon field's presence. And there's tantalizing, if controversial, evidence. Certain anomalies in the orbits of distant spacecraft like NASA Pioneer probes show tiny deviations from predicted paths, exactly the kind of hiccup you'd expect if a hidden field were tweaking gravity's rules in deep space. But the wildest idea: chameleon fields might not just hide, they could rewrite gravity altogether. Modified Newtonian dynamics, or MUND, is an alternative theory suggesting gravity behaves differently at cosmic scales than our equations predict. While controversial, it's gained traction as a potential dark matter workaround. If chameleon fields are real, they could be the missing link, subtly adjusting gravity's strength without the need for invisible particles. Picture a universe where gravity isn't a fixed force, but one that shifts based on hidden fields we're only beginning to sense. Yet skeptics argue these fields are too convenient, a theoretical bandage slapped onto gaps in our understanding. Without direct detection, they remain in the realm of what if. But that's the beauty of theoretical physics. Sometimes the wildest ideas, the ones that seem to dodge every test, turn out to be real. Whether chameleon fields exist or not, the search itself is stretching our imagination, forcing us to ask, how many layers of reality are still out there waiting to be uncovered? And how many of them are hiding in plain sight? Gravity isn't just a force, it's a conversation between masses, whispered across the universe through ripples in space-time itself. But what if those ripples aren't just echoes of colliding black holes? What if some were forged in the universe's first moments, woven into existence by hidden tensor fields we've yet to fully understand? These aren't ordinary fields like electromagnetism. Tensor fields are geometric, shaping space-time not just with pushes and pulls, but by twisting and stretching the very fabric of reality. And their fingerprints might be hiding in the faintest tremors of gravitational waves passing through Earth right now. Think of space-time as a trampoline. Drop a bowling ball onto it and the fabric dips. Roll a marble nearby and it spirals toward the heavier object. That's gravity as we know it, but tensor fields. They're like invisible hands beneath the trampoline, not just bending the surface but warping its underlying structure. In the early universe, these fields could have vibrated with unimaginable energy, sending out gravitational waves so powerful they're still detectable today as a cosmic hum. These wouldn't be the high-frequency waves from black hole mergers we've observed recently. These would be primordial, a bass note from the Big Bang's first symphony. The hunt for these ancient waves is heating up. Experiments like the Laser Interferometer Gravitational Wave Observatory LIGO are tuning their instruments to catch lower frequencies, while space-based detectors like the proposed Laser Interferometer Space Antenna, or LISA, aim to sense oscillations too subtle for Earth's noisy environment. But here's the twist: if we find them, they might not match predictions from standard inflation. Some models suggest tensor fields could have generated waves with unique polarizations, patterns that would point to exotic physics beyond Einstein's relativity. It's like discovering a song where you expected a drumbeat, only to hear an entirely new instrument, and the implications stretch beyond our universe. If tensor fields sculpted primordial gravitational waves, their behavior could hint at extra dimensions, hidden layers of reality where these fields interact in ways we can't directly see. Imagine a cosmic loom weaving threads through higher dimensions, with the vibrations spilling into our own space-time as gravitational ripples. This isn't just theoretical eye candy. Certain patterns in these waves could support string theory's vision of a multiverse, where our universe is one bubble among countless others, each with its own unique physics. But the real showstopper, tensor fields, might explain why gravity is so weak compared to other forces. While electromagnetism can yank a paperclip off a desk from inches away, gravity needs a planet's worth of mass to exert a similar pull. If tensor fields are diluting gravity's strength by leaking into extra dimensions, it would solve one of physics' most perplexing hierarchy problems. Picture a garden hose spraying water. If half the streams vanish into unseen holes, the remaining flow seems weaker, even though nothing's wrong with the source. Of course, not all scientists are convinced. Critics argue that primordial gravitational waves could have simpler origins, like violent phase transitions in the early universe. Others caution that tensor fields are mathematically elegant but lack smoking gun evidence. Yet that's the thrill of the chase. Every new gravitational wave detection peels back another layer of possibility. Whether these hidden fields are real or not, their theoretical shadow pushes us to ask bigger questions. What if gravity isn't fundamental but emergent? What if space-time isn't a stage but a player in its own drama? The answers might be written in waves we're just learning to hear. What if the laws of nature aren't fixed but learn and evolve over time? That's the radical premise behind Rupert Sheldrake's morphic field hypothesis, a theory so controversial, it's been called everything from groundbreaking to pseudoscience. At its core, this idea suggests there's an invisible, non-physical field that shapes not just biology, but behavior and even the structure of reality itself. Forget traditional physics for a moment. Imagine a living, responsive universe where habits, whether in crystals, cells, or human minds, ripple across this field, making patterns easier to repeat over time. It's as if nature has a memory. Take something as simple as a snowflake. Under Sheldrake's model, the first time water molecules froze into a particular hexagonal pattern, it was a fluke. But as that pattern repeated across millennia, the morphic field remembered it, making future snowflakes more likely to form the same way. This isn't just about ice crystals. The theory extends to animal instincts, like how monarch butterflies navigate migration routes they've never flown, or why lab rats worldwide seem to learn mazes faster over generations, even when isolated from each other. Sheldrake argues these aren't coincidences, but evidence of a field transmitting information outside known physical laws. Now, tie this to quantum physics and things get even stranger. Quantum entanglement shows particles can instantaneously influence each other across vast distances, defying classical notions of space and time. Morphic fields, Sheldrake suggests, could be the hidden medium enabling this, a cosmic web connecting seemingly separate events through resonance rather than force. Picture a school of fish changing direction in perfect sync. There's no visible signal, no leader calling the shots, they just know. If consciousness itself taps into this field, it might explain everything from collective human intuition to the eerie accuracy of certain gut feelings. Of course, mainstream science remains skeptical. Critics point out the lack of measurable energy or detectable particles associated with morphic fields, labeling them untestable and therefore unscientific. Yet some quantum biologists see parallels. The way proteins fold, for instance, can't always be predicted by chemistry alone. There's an almost intelligent efficiency to the process, as if guided by an invisible hand. Could that hand be a morphic field? Even if Sheldrake's specific model isn't correct, the questions it raises are electrifying. What if evolution isn't just random mutations, but a dialogue between organisms and some deeper, organizing principle? The implications ripple into human experience too. Consider the placebo effect, where belief alone triggers healing, or the way cultural myths and archetypes recur across unconnected civilizations. Sheldrake would argue these aren't accidents, but echoes of the morphic fields influence a kind of cosmic habit formation. And let's not forget the countless anecdotal reports of pets anticipating their owner's return, or humans sensing distant tragedies. Science often dismisses these as coincidence, but what if they're glimpses of a larger, interconnected reality? Whether morphic fields exist or not, they challenge us to rethink the boundaries of biology, physics, and consciousness. In a universe teeming with dark matter, quantum weirdness, and unexplained cosmic forces, dismissing unconventional ideas outright might be the riskiest stance of all. After all, every scientific revolution began as heresy. The real question isn't whether Sheldrake's theory is provable today. It's whether we're open to the possibility that reality might be far more mysterious, far more alive than our current models suggest. Even in complete darkness in the emptiest reaches of space, there's a seething undercurrent of energy, a restless hum that never quiets. This isn't poetic exaggeration. Quantum physics tells us that what we call a vacuum is anything but empty. It's a Chinese letter C of zero-point energy, where particles flicker in and out of existence so fast they defy every intuition about stillness. The energy tied to these fleeting fluctuations isn't small. In fact, if you could tap just a cubic meter of seemingly empty space, the zero-point energy inside would theoretically be enough to boil Earth's oceans. Twice, this isn't science fiction. Zero-point energy is a real, measurable consequence of Heisenberg's uncertainty principle, the idea that you can never perfectly pin down a particle's position and momentum at once. There's always a tiny wiggle room, a minimum energy that particles can't drop below. No matter how cold the universe gets, picture a guitar string that never stops vibrating, even when untouched. At the quantum level, space itself is strung with these invisible vibrations, a background static that never fades. Now, here's where it gets wild. Some theories suggest this energy could be harnessed, unlocking a power source beyond anything we've dreamed. Imagine spacecraft propelled by the vacuum itself, engines that don't need fuel tanks but ride the quantum ripples of space-time. The idea isn't entirely far-fetched. Experiments like the Casimir effect show zero-point energy's tangible force. Place two ultra-close metal plates in a vacuum, and the quantum fluctuations outside push them together slightly, as if the universe itself is squeezing them. It's proof that this energy can, in principle, do work, but the obstacles are staggering. Zero-point energy is everywhere, but it's also perfectly balanced like a stretched rubber band with no loose end to pull. Extracting usable energy from it would mean breaking that symmetry, and physics stubbornly resists such free lunches. Some proposals, like the Alcubierre warp drive, flirt with the idea of manipulating this energy to bend space-time, creating a bubble that moves faster than light. The math checks out barely, but the energy requirements are astronomical and the engineering is pure speculation. The deeper mystery, zero-point energy, might already be shaping the cosmos. Some calculations suggest it's the hidden engine behind dark energy, the force accelerating the universe's expansion. If true, then this omnipresent energy isn't just a curiosity, it's actively rewriting the fate of everything. Yet here's the paradox: while zero-point energy is infinite in theory, we're surrounded by it, bathed in it, and still utterly powerless to touch it. It's like standing in a hurricane with no sails. For now, the dream of vacuum energy remains just that, a dream. But the pursuit has already reshaped physics, pushing us to ask whether empty space is the most misleading term in science. Whether we harness it or not, zero-point energy forces us to confront a profound truth. The universe is never truly at rest. Even in silence, even in void, there's a whisper of creation and destruction, a reminder that reality's foundations are far stranger than they appear. Twist a wet towel, and you can see the tension ripple through its fibers. But what if space itself does something similar? That's the provocative idea behind torsion fields, a hidden layer of space-time geometry that could explain some of the cosmos' most baffling behaviors. Unlike the smooth curves of Einstein's relativity, torsion introduces a spiraling twist to the fabric of reality, like a corkscrew winding through the universe's structure. And if real, it might hold answers to mysteries that gravity alone can't solve. Take the dark flow, an eerie phenomenon where entire galaxy clusters seem to drift in the same direction, as if tugged by some invisible current. The standard model chalks it up to statistical flukes, but torsion offers a wilder explanation. That space-time itself is coiled on cosmic scales, creating subtle directional biases we're only now detecting. Picture a river with hidden whirlpools while the water mostly flows forward. The swirls beneath the surface nudge objects in unexpected ways. Torsion fields could be those whirlpools, warping the paths of galaxies without any dark matter or energy required. This isn't just speculation. Russian physicist Nikolai Kozyrev spent decades experimenting with torsion, claiming it could transmit energy instantaneously, a heresy in Einstein's speed of light-limited universe. His experiments, though controversial, suggested objects could influence each other through spacetime's twisted geometry faster than light should allow. Modern extensions of his work propose that torsion might explain quantum entanglements, spooky action at a distance, where particles mirror each other's states across light years. Instead of magic, it'd be spacetime's hidden spirals doing the work, like threads connecting distant puppets. The math gets even stranger when you scale up. Some torsion models predict that rotating black holes could twist spacetime around them into cosmic tornadoes, funneling matter and energy along spiral paths we've mistaken for jets. Observations of quasars' supermassive black holes spearing the universe with plasma beams show structures that look suspiciously like helical streams, as if space itself is writhing under their spin. If torsion is real, these black holes aren't just gravity wells, they're spacetime's ultimate drill bits boring tunnels through reality, yet the boldest idea. Torsion might unify the very large and the very small. Quantum physics treats particles as points, but string theory imagines them as vibrating loops. Torsion fields could be the missing link, the geometric glue that gives those loops their twist, bridging the gap between the smooth cosmos and the quantum fray. It's a dizzying thought that every electron's spin, every galaxy's dance, might trace back to the same underlying spiral etched into the universe's blueprint. Of course, mainstream science remains cautious. Torsion theories often flirt with fringe ideas like free energy or anti-gravity, muddying their credibility. But as detectors grow more sensitive, able to measure spacetime's subtlest tremors, we might finally catch torsion in the act. Whether it's a cosmic illusion or a fundamental force, one thing's clear: the universe has more twists in its plot than we ever imagined. What if the apparent chaos of quantum particles isn't random at all, but guided by an invisible hand? This was physicist David Bohm's daring proposition, a hidden layer of reality he called the implicate order. In this shadow realm, particles aren't isolated billiard balls bouncing unpredictably. They're more like droplets in a flowing river carried along by a deeper, invisible current, a quantum field so all-encompassing, it connects every particle in the universe instantly, like threads in a cosmic tapestry. Bohm's vision clashed head-on with mainstream quantum theory, where traditional interpretations see particles as probability clouds collapsing into definite states only when observed. Bohm argued for determinism. Beneath the apparent randomness, he believed an undetectable pilot wave steers particles along precise paths. Picture a surfer riding a wave. The wave's unseen energy dictates the surfer's motion, even though we only see the person gliding. That's how particles behave in Bohm's model, dancing to the rhythm of a hidden quantum field we can't directly measure. The implications are staggering. If Bohm was right, quantum entanglement, where particles mirror each other's states across vast distances, isn't spooky action at a distance, but evidence of this deeper connectivity. Two electrons could instantly sync not because they're magically linked, but because they're both tethered to the same underlying field, like buoys bobbing on opposite ends of a submerged net. Even the famous double-slit experiment, where particles act as both waves and particles, gets a new explanation. The wave isn't just probability, it's the pilot wave itself, guiding particles to create interference patterns. Critics dismissed Bohm's ideas as untestable metaphysics. After all, if the pilot wave can't be detected, how do we prove it exists? But supporters point to eerie parallels in fluid dynamics, where oil droplets bouncing on vibrating surfaces eerily mimic quantum behavior, guided by waves they themselves generate. These experiments suggest Bohm's hidden variables might not be so far-fetched, just veiled by scales we're only beginning to probe, the most radical part. Bohm saw the implicate order as more than physics, it was a philosophical revolution. In his view, separation itself might be an illusion, with the entire universe unfolding from this hidden fabric like a hologram projecting reality. Particles, planets, even human thoughts could be ripples on a single, unbroken field. It's a concept that blurs the line between science and spirituality, hinting at a universe far more interconnected than our senses perceive. Yet the debate rages on. Modern quantum theory prefers the cleaner math of probabilities over Bohm's clunky pilot waves. But as we stumble upon quantum weirdness that defies conventional explanations, like particles that retroactively change their past behavior, Bohm's ghost whispers from the margins. What if the answers were hidden in plain sight all along, woven into the folds of reality itself? Deep in the archives of ancient Vedic texts, there's a concept as old as human thought itself. The Akashic records, a cosmic library said to hold every event, thought, and vibration that ever was. Fast forward to modern physics, and you'll find eerily similar ideas bubbling up in cutting-edge theories. The notion that information, once created, might never truly vanish. What if these two worlds, mysticism and science, are pointing toward the same startling possibility, that the universe itself remembers? Enter the Akashic field, a hypothetical information field woven into the fabric of space-time. Unlike physical forces we can measure, this wouldn't be a field of energy but of data, an imprint left behind by every particle collision, every supernova's burst, even every fleeting human thought. Think of it like the universe's DNA, encoding not just the present but echoes of the past and blueprints of the future. Some quantum physicists argue this isn't just poetic metaphor. The holographic principle, born from black hole thermodynamics, suggests all information within a volume of space might be stored on its boundary, like a three-dimensional movie projected from a two-dimensional screen. If true, the cosmos itself could be a dynamic hologram with the Akashic field as its storage medium. Here's where it gets uncanny. Experiments in quantum erasure show that particles can seemingly, retroactively, change their behavior based on future observations, as if information flows backward through time. Then there's the controversial work of scientists like Erwin Laszlo, who proposed that the Akashic field could explain collective consciousness, morphic resonance, even the uncanny accuracy of intuition. Imagine dropping a pebble into a pond. The ripples spread outward, but the pond remembers the disturbance long after the pebble sinks. Now scale that up. Every event in history sending ripples through this field, subtly influencing what comes next. But how could we test something so abstract? Clues might lie in the cosmic microwave background, the afterglow of the Big Bang. Some theorists suggest faint anomalies in this radiation could be information imprints, like cosmic fingerprints left by earlier universes in a cyclical multiverse. Others point to quantum computers, where qubits maintain superposition states, potentially tapping into this field's vast informational web. Even human memory itself bends the rules. Cases of savants recalling impossibly precise details, or near-death experiences describing events they shouldn't know, hint at a layer of reality where information defies conventional storage. Skeptics, of course, dismiss the Akashic field as wishful thinking, a modern repackaging of spiritual ideas with no empirical teeth. Yet the same was once said of gravitational waves, black holes, even the Big Bang. What makes this theory tantalizing isn't just its audacity, but its ability to bridge gaps between disciplines that rarely speak. Quantum physics whispering to neuroscience, cosmology nodding to ancient mysticism. Whether the Akashic field is real or not, it challenges us to ask a profound question. If information is truly fundamental to reality, might the universe itself be conscious? The answer, if it exists, is written somewhere in the fabric of space-time. We just haven't learned to read it yet. Imagine stepping close to a movie screen until your nose nearly touches it suddenly. The picture dissolves into meaningless dots. But step back, and those flat, two-dimensional pixels resolve into a vivid three-dimensional world. Now stretch that idea across the cosmos. The holographic principle suggests our universe might work the same way, that every star, planet, and even your own hands could be a three-dimensional projection from information encoded on a distant, two-dimensional surface. And the strangest part, the best evidence for this might lie in the darkest objects in existence, black holes. Here's how it works. When matter falls into a black hole, it seems to vanish forever, violating a core rule of physics: information can't be destroyed. But in the 1970s, physicist Jacob Bekenstein calculated that black holes must preserve information by encoding it on their event horizons, the point of no return. Think of it like a cosmic hard drive. Every atom swallowed gets stamped onto the black hole's surface as quantum bits or qubits, much like a DVD stores a movie as microscopic bits. Later, Stephen Hawking showed these black holes slowly evaporate, radiating energy. The puzzle: that radiation appeared random, implying the original information was lost. But if the holographic principle is correct, the data isn't gone. It's just translated, imprinted onto the event horizon in a form we don't yet understand. This isn't just about black holes. The math suggests the entire universe could operate the same way. Picture Earth's surface covered in tiny pixels, each one Planck length size, the smallest possible unit in physics. The information needed to describe everything inside our planet, from molten core to mountain peaks, might fit perfectly onto those surface pixels. It sounds impossible, but holograms do this trick every day. Shine a laser through a flat, patterned film, and a three-dimensional image appears in midair. The universe, according to this theory, might be the ultimate hologram, with hidden fields acting as the film that projects reality. What's wild is that we might already have evidence. The cosmic microwave background, the afterglow of the Big Bang, shows temperature fluctuations that match predictions from holographic models. These patterns look like interference, as if the universe itself is a projection from some deeper layer. Even quantum entanglement fits eerily well. Particles instantly influencing each other across vast distances could be illusions, their connection pre-written on that two-dimensional boundary, like actors following a shared script. But the real mind-bender: if the holographic principle is true, then time and space aren't fundamental, they're emergent, like the illusion of movement in a flipbook. The universe wouldn't happen in three dimensions. It would be a dynamic interplay of information on a hidden field we can't see or touch. It's a humbling thought that everything you experience, the weight of your coffee cup, the glow of a sunset, might just be shadows dancing on the edge of something far stranger, a cosmic code we're only beginning to crack. Paul Dirac once scribbled an equation that seemed to break reality. In 1928, his math revealed something impossible: electrons with negative energy. Not just a negative charge, but energy levels below zero, as if particles could be less than nothing. To make sense of it, he proposed a radical solution. The entire universe might be submerged in an invisible ocean of these ghostly electrons, a churning Dirac sea so dense it normally escapes detection. Imagine filling a bathtub to the brim, then trying to add one more drop. The water that spills out isn't the new drop, it's the displacement of what was already there. Dirac's sea worked the same way. When energy excites this hidden ocean, it doesn't create a negative electron. It leaves behind a hole that behaves like its opposite, antimatter. This wasn't just poetic imagery. When Carl Anderson detected the positron in 1932, an electron's antimatter twin, it was the first tangible proof Dirac's sea might be real. But here's where modern physics takes a surreal turn. Today, we describe antimatter not as holes in a cosmic ocean, but through quantum field theory's lens. All of space is filled with dynamic fields, and particles are mere ripples on their surface. What Dirac called the sea, we now frame as the electron field's baseline state. Yet the echoes of his idea persist. When a gamma-ray photon spontaneously splits into an electron and positron, it's almost as if the photon dips into the Dirac sea, pulling up a particle and leaving an anti-particle in its wake. The implications ripple across the cosmos. If Dirac's sea exists even metaphorically, it might explain why the universe isn't just a soup of matter and antimatter annihilating each other. Some theories suggest slight asymmetries in this hidden sea could have tilted the early universe toward matter's dominance. Picture two nearly identical staircases, one with a single step slightly higher than the rest. Over time, more particles might trip into matter's direction, leaving antimatter as the rare exception. And then there's the haunting possibility that Dirac's sea isn't entirely metaphorical. In quantum electrodynamics, the vacuum isn't empty. It's a frothing brew of virtual particle pairs constantly forming and annihilating. These fleeting fluctuations are eerily reminiscent of Dirac's churning ocean, just reinterpreted through modern math. Some physicists even speculate that tapping into this sea's energy could theoretically unlock propulsion systems straight out of science fiction, like engines that harness particle-antiparticle creation from the quantum foam itself. Yet the Dirac sea's true legacy might be philosophical. It forced physicists to confront a truth that still unsettles us. What we call nothing is never truly vacant. Whether framed as fields, virtual particles, or a cosmic ocean, the universe refuses to sit still. Even in the darkest void, hidden layers churn beneath the surface, shaping everything from the atoms in your hands to the fate of galaxies. Dirac's equation didn't just predict antimatter, it hinted that reality is far richer, far stranger than our senses will ever let us see. Fred Hoyle looked at the expanding universe and saw a problem. If galaxies were racing apart, why didn't space grow emptier over time? His audacious answer flew in the face of the Big Bang, a hidden force he called the sea field, quietly weaving new matter into existence to keep the cosmos eternally balanced. Picture a bathtub with the drain open, water flows out, but an unseen faucet drips just enough to maintain the perfect level. That was Hoyle's vision. A universe with no beginning, no end, forever replenishing itself through this mysterious creative field. The math was elegant. As galaxies drifted apart, the sea field would generate hydrogen atoms in the voids between them, not in explosive bursts but in a slow, steady trickle. 1 atom per cubic meter every few billion years might not sound like much, but across the vastness of space, it added up. This wasn't just tinkering with physics, it was a full rewrite of cosmic history. While rivals argued for a fiery origin in the Big Bang, Hoyle's steady-state model offered an infinite universe, always renewing itself with no need for a starting gun. But the theory had cracks. For the sea field to work, it had to violate one of science's most sacred laws, conservation of energy. Energy can't be created or destroyed, yet here was a field doing exactly that, conjuring matter from nothing. Hoyle argued the sea field's energy might come from the expansion of space itself, a loophole that left many physicists unconvinced. Then came the knockout blow, the discovery of the cosmic microwave background in 1965. This faint glow, the afterimage of the Big Bang's primordial fireball, was the smoking gun the steady-state model couldn't explain, yet Hoyle's ideas weren't entirely wrong. Modern cosmology borrows eerie echoes of the sea field in concepts like dark energy, an unseen force stretching space and effectively creating new volume. Even the notion of continuous creation resurfaces in quantum field theory, where virtual particles blink into existence from empty space. The difference. Today's physics anchors these phenomena in measurable mechanisms, not ad hoc fields. What remains fascinating isn't just the theory's rise and fall, but its daring reimagining of reality. Hoyle refused to accept a universe with an expiration date, betting instead on hidden forces that kept the cosmic scales balanced. In the end, the evidence favored the Big Bang, but the sea field's ghost lingers, a reminder that sometimes the boldest wrong ideas light the path to the right ones. What if time isn't just a ticking clock, but a hidden field shaping reality itself? Most of us experience time as an unstoppable river, always flowing forward, never backward. But physics has never fully explained why. The laws of motion work just as well in reverse, yet eggs don't unscramble and memories don't unform. This stubborn one-way street is called the arrow of time, and some theories suggest it might be driven by a secret player, a time field. Think of entropy as nature's way of stirring cream into coffee. Left alone, the mixture always spreads toward disorder. That's the second law of thermodynamics. But what if entropy isn't the full story? Quantum gravity researchers propose that beneath the familiar march of time, there could be a field that biases the universe toward increasing complexity. Picture a hidden slope tilting the cosmic playing field, making certain outcomes like the formation of stars or the firing of neurons more likely than their reverse. This wouldn't be a force like gravity, but something subtler, a framework that makes the past fundamentally different from the future, not just in our perception, but in the fabric of reality itself. The clues might lie in black holes. When matter crosses an event horizon, it scrambles information so thoroughly that even time's arrow seems to blur. Some models suggest this chaos hints at a deeper structure, a time field that warps near singularities, much like gravity warps space. If true, it could explain why time appears to emerge from the quantum foam only on larger scales, like a mirage solidifying as you step back. Even quantum mechanics dances with this idea. Particles like the kaon violate time symmetry, behaving differently when the clock runs backward. Could these microscopic quirks be echoes of a field that privileges one temporal direction? Experiments with entangled particles add to the mystery. When two particles sync instantly across distances, does their connection transcend time entirely? Or is some hidden field mediating their bond outside our linear experience? The boldest theories go further, suggesting the time field isn't universal but local, a patchwork where time flows at different angles across the cosmos. In regions of extreme gravity or near light speed, its influence might twist, allowing hypothetical time loops or even stasis zones where entropy stands still. It's a dizzying thought that the steady tick we take for granted could be as malleable as spacetime itself, shaped by forces we're only beginning to fathom. Whether the time field is real or not, its theoretical shadow forces us to confront a profound truth. Time might not be the backdrop of reality, but an active participant, a hidden architect quietly sculpting the universe's unfolding story. And if we ever learn to read its language, we might finally understand why the past stays past and the future remains forever just out of reach. Consciousness has always been the ghost in the machine of physics, a phenomenon we can't measure, yet undeniably shapes our reality. What if this elusive quality isn't confined to our brains but woven into the cosmos itself? That's the radical proposition behind the noetic field, a hidden layer where mind and matter might fundamentally intertwine. Unlike gravitational or electromagnetic fields, this wouldn't just influence particles. It could be the hidden substrate linking quantum weirdness to the tapestry of subjective experience. Take the observer effect in quantum mechanics, where particles seem to choose their state only when measured. Mainstream science treats this as a mathematical quirk, but noetic field theory suggests something deeper. That consciousness isn't a passive witness, but an active participant in reality's unfolding. Picture a cosmic game of telephone where the act of observation resonates through this field, subtly shaping outcomes like a pebble disturbing a pond's surface. Experiments like the double-slit test take on new meaning. Perhaps particles don't collapse into states randomly, but respond to the presence of a mind embedded in the noetic web. The implications ripple into neuroscience. Near-death experiences report lucid awareness during clinical brain death, while studies on meditation show practitioners can influence random number generators at statistically improbable rates. Skeptics dismiss these as anomalies, but noetic field theorists argue they're glimpses of consciousness extending beyond the skull, interacting with a field that permeates spacetime. Even collective intuition, the uncanny accuracy of gut feelings shared across cultures, might trace back to this interconnected layer, like radios tuned to the same hidden frequency. Here's where it gets truly paradigm-shifting. If the noetic field exists, it could bridge the hard problem of consciousness, why subjective experience arises from mere neural activity. Instead of emerging from brain chemistry alone, consciousness might be a fundamental feature of reality, channeled through biological structures but not confined to them. Think of the brain as a receiver, not a generator, picking up signals from this deeper field like a television translating broadcast waves into images. This would explain why altering brain chemistry changes perception, but doesn't erase awareness itself. Critics, of course, demand harder proof. Labs are now testing noetic effects by isolating consciousness from known physical forces, using protocols like blinded intention experiments with quantum systems. Early results are contentious, but tantalizing. Some show slight deviations from statistical noise when focused human intent is applied to sensitive detectors. It's as if the noetic field signal is faint, detectable only at the knife's edge of measurement error. Whether proven or not, this theory challenges us to rethink the boundaries of science and self. If consciousness truly interacts with hidden fields, then reality isn't just out there. It's a dance between observer and observed, a cosmic feedback loop where the act of seeing might itself be a creative force. And that raises a question far bigger than any experiment. If the universe is shaped by the minds within it, what happens when we collectively learn to listen and reply? Picture a universe filled with an invisible, intangible substance, a medium so subtle that light waves ripple through it like sound through air. This was the luminiferous ether, the 19th century's answer to one of physics' biggest puzzles. How could light travel as a wave if space was truly empty? The idea made perfect sense at the time. After all, every other wave needed a medium, water for ocean waves, air for sound, so why wouldn't light? Yet by the early 20th century, the ether was tossed into the dustbin of scientific history, discredited by Michelson and Morley's failed experiments to detect it and Einstein's relativity, which rendered it unnecessary. But here's the twist. What if the ether wasn't entirely wrong, just misunderstood? Modern quantum field theory paints a picture that would have made ether enthusiasts gasp. Empty space, we now know, is anything but empty. It's a seething quantum foam, buzzing with virtual particles and crisscrossed by fundamental fields, the Higgs field, electromagnetic fields, even the gravitational field. These fields permeate every corner of the universe, filling the void with an invisible lattice of energy and potential. In this light, the old ether wasn't a foolish idea, it was a rough draft of a deeper truth. The ether didn't vanish, it just got upgraded. Consider the Higgs field. Like the classical ether, it's an all-pervading presence that interacts with particles, giving them mass as they move through it. The difference, the Higgs doesn't drag on objects or create a preferred reference frame, the fatal flaws of the original ether. Instead, it's a dynamic field that operates within relativity's rules. It's as if the 19th century physicists sketched the outline of a tree, and we've since filled in the roots, branches, and leaves. Even stranger is the quantum vacuum. Zero-point energy ensures that space is never truly empty, but a frenetic dance of particles flickering in and out of existence. This vacuum energy behaves like a fluid, not unlike the ether's hypothetical medium, except it's relativistic and obeys quantum mechanics. Some theorists argue that dark energy, the mysterious force accelerating the universe's expansion, might even be a modern echo of the ether's resurgence, an omnipresent energy woven into space itself. So was the ether right for the wrong reasons? In a way, yes. The original concept was built on flawed assumptions, but its core intuition, that space isn't passive but alive with unseen activity, was eerily prescient. Today's fields are mathematically precise, rigorously tested, and light years ahead of the old ether in explanatory power. Yet the ghost of the idea lingers, a reminder that sometimes the biggest mistakes in science aren't dead ends, but signposts pointing toward truths we aren't yet ready to see. Consider the universe as the ultimate supercomputer, where every particle, every force, and even space-time itself might be pixels in a cosmic digital display. This isn't science fiction, it's the essence of the information field theory, the mind-bending idea that reality isn't built on matter or energy, but on something far more fundamental: bits. Not the silicon chips in your laptop, but irreducible units of information woven into the fabric of existence, like the ones and zeros underlying a virtual world. And the strangest part, the clues to this theory aren't hidden in some distant galaxy, but in the paradoxes of black holes and the spooky connections of quantum entanglement. Take black holes first. When matter vanishes beyond an event horizon, it doesn't just disappear, it leaves behind a ghostly fingerprint encoded on the surface of the black hole itself. Physicists call this the holographic principle, and it suggests that all the information about what fell in gets compressed into a two-dimensional quantum script on the horizon's edge. It's as if the black hole is a cosmic USB drive, storing three-dimensional events on a two-dimensional surface. If true, then the universe might work the same way, with the information field acting as the ultimate hard drive, rendering our 3D reality as a projection from a deeper informational layer. Now zoom into the quantum scale, where entanglement defies every classical notion of distance. Two particles can instantaneously mirror each other's states, no matter how far apart they are, a phenomenon Einstein famously called spooky action at a distance. But if information is the bedrock of reality, entanglement isn't so spooky. It's more like two cells in a spreadsheet linked by an invisible formula. Change one, and the other updates automatically, not because of some mysterious force, but because they're part of the same underlying code. The implications ripple outward. If information is fundamental, then the laws of physics might just be algorithms, cosmic software running on the universe's hardware. Even time and space could emerge from how information is processed and connected, like the illusion of movement in a flipbook. Some theorists take this further, suggesting that black holes aren't just information storers but processors, crunching data in ways we can't yet fathom. It's a radical shift. Instead of asking what the universe is made of, we might need to ask what it's computing. Skeptics, of course, push back. If reality is information, what's processing it? Who or what wrote the code? These questions veer into philosophy, but experiments are already probing the edges. Quantum computers manipulate information in ways classical physics can't explain, hinting at rules beyond atoms and forces. And if we ever detect gravitational waves from primordial black holes, their patterns might reveal the universe's information architecture like cosmic QR codes etched into space-time. Whether the information field is real or not, it reframes our place in the cosmos. We're not just observers of reality. We might be participants in a vast, unfolding computation, one where every thought, every measurement, even this very sentence could be part of the data stream. And somewhere in the quantum noise or the silent spin of black holes, the universe's source code might still be waiting to be deciphered. Phantom energy isn't just another cosmic mystery, it's a theoretical field with the power to unravel reality itself. Unlike dark energy, which gently accelerates cosmic expansion, phantom energy grows stronger over time, an unstoppable force that could stretch space-time until it snaps. Picture a rubber band pulled tighter and tighter, not just thinning but fraying at the edges until pop. The fabric of existence itself tears apart. This is the Big Rip, one of the most violent endings ever imagined for the universe, and it all hinges on a field we've never directly seen. The math behind phantom energy is as elegant as it is terrifying. The key lies in its equation of state, a measure of how its pressure relates to its energy density. For most forms of energy, this value hovers around -1, but phantom energy, it plunges lower, pushing the field's repulsive gravity into overdrive. The result, expansion doesn't just continue, it accelerates exponentially like a car with a gas pedal glued to the floor. Galaxies would first vanish over the cosmic horizon, then galaxy clusters, until even atoms are wrenched apart as the field's grip overwhelms the very forces holding matter together. What's chilling is how little it would take to trigger this scenario. If phantom energy makes up just a fraction more of the universe's density than current dark energy estimates, its influence could dominate within tens of billions of years, a blink in cosmic terms. Telescopes scanning distant supernova have already spotted hints of something odd, expansion rates that don't quite align with standard dark energy models. Could these be phantom energy's first whispers? Yet the wildest implications aren't just about the end, they're about beginnings. Some theories suggest phantom energy might have played a role in cosmic inflation, the universe's explosive early growth. If a similar field drove that epoch, it could mean the Big Bang and the Big Rip are bookends of the same phenomenon, space-time stretched thin at both ends of history. Even black holes wouldn't be safe. In a Big Rip scenario, their event horizons would dissolve before the stars themselves, spitting out trapped information in one final burst of radiation, a last gasp before everything, everywhere, dissolves into infinite, disconnected emptiness. The irony, phantom energy might be impossible to detect directly until it's too late. Like a shadow creeping across the cosmos, its effects only become obvious when they're irreversible. Yet that hasn't stopped scientists from hunting for clues. By mapping the universe's large-scale structure and refining measurements of dark energy's equation of state, we might one day spot the telltale signs of this phantom lurking in the data. Until then, it remains a haunting reminder the universe's finale could be far stranger, far more violent than we ever dared to dream. Magnets are everywhere, in your phone, your headphones, even the Earth itself, and they all share a strange quirk. They come with two inseparable poles, north and south. No matter how many times you split a magnet, you'll always end up with a new pair of poles. But what if nature hid a secret, a lone magnetic charge, a north without a south, drifting through the cosmos like an electrical charge untethered from its opposite? This elusive phantom, the magnetic monopole, isn't just a curiosity. It could be the key to unlocking grand unified theories, stitching together the fundamental forces of the universe. The hunt for monopoles began with a stroke of genius from physicist Paul Dirac. In 1931, he showed that if even one magnetic monopole existed, it would explain why electric charge comes in neat, discrete units, like cosmic receipts proving a deeper symmetry in nature. The math was airtight, but for decades no one could find the real thing. Then came grand unified theories which predict these solitary poles should have formed in unimaginable numbers during the universe's first split second, when electromagnetism and the nuclear forces were still one. Picture a primordial superforce shattering like glass, its fractures spraying monopoles across the infant cosmos. If just a handful survived, they might still be out there, threading space with unseen magnetic fields. Here's where it gets cosmic. monopoles wouldn't just drift aimlessly, they could cluster into vast, invisible structures like galaxies made of pure magnetism. These monopole fields might weave through galaxy clusters, subtly bending cosmic rays or tweaking the orbits of stars. Some theorists even suggest they could see dark matter's gravitational scaffolding, their mass and hidden interactions sculpting the universe's large-scale structure. Imagine a web of magnetic highways crisscrossing the void, guiding particles and energies we're only beginning to sense. Yet the real revolution would come if we ever trapped one. Monopoles are time capsules from the universe's hottest, most energetic moment. Their very existence would confirm that the fundamental forces were once unified. Studying their properties could reveal the energy scale of that unification, like cosmic archaeologists dusting off a relic from reality's first trillionth of a second. And the implications ripple deeper. If monopoles interact with the Higgs field or dark energy, they might help explain why the universe's constants are so finely tuned for life. The search is fiercer than ever. Experiments buried deep underground, shielded from cosmic noise, scan for monopoles' telltale ionizing trails. Particle colliders recreate extreme energies, hoping to spark these relics into existence. Even ancient mica crystals are scrutinized for microscopic scars that could only come from a monopole's passage over millions of years. So far, nothing. But absence isn't disapproval. It might just mean monopoles are rarer, heavier, or stranger than we predicted. Whether we find them or not, magnetic monopoles force us to confront a humbling truth. The universe's blueprints might still have pages we've never turned. And somewhere in the vast magnetic tapestry of space, a single, lonely pole could be waiting, a cosmic key to the grand unification of everything. Deep in the equations of supersymmetry, a theory that doubles the universe's known particles, lurks a ghost. The neutralino, a hypothetical particle born from the dance between supersymmetric partners, could be far more than mathematical whimsy. It might be the invisible hand shaping galaxies, the missing puzzle piece of dark matter, and the key to uncovering hidden fields woven through the cosmos. Imagine a cosmic game of shadows where every particle we know has a heavier, unseen twin. The neutralino, stable and nearly massless, would be the lightest of these twins, elusive enough to evade detection, yet abundant enough to sculpt the universe's largest structures. What makes neutralinos so compelling is their dual nature. Unlike other dark matter candidates, they're not just placeholders for gravity's grip on galaxies. They're predicted by supersymmetry's elegant math, which aims to unify nature's forces under a single framework. If they exist, neutralinos would be their own antiparticles, annihilating each other in flashes of gamma rays when they collide. Fermi telescope observations of mysterious gamma-ray excesses near the Milky Way center have sparked debates. Could these be the dying breaths of neutralino annihilations, whispers from a shadow universe of particles we've yet to touch? The hunt hinges on their interaction with hidden fields. Neutralinos don't just float passively through space, they're thought to couple with the Higgs field, the same cosmic scaffold that gives particles mass. Some models suggest they might also interact with undiscovered fields, ones that could mediate forces beyond the standard model. Picture a vast, invisible network of fields and particles, influencing each other in ways that leave only faint imprints on our detectors. Experiments like the Large Hadron Collider are probing higher energies, hoping to spot the telltale energy gaps where neutralinos might be hiding. Meanwhile, deep underground labs, shielded from cosmic noise, wait for the rare tremor of a neutralino bumping into an atomic nucleus. But the stakes are higher than just ticking a box in particle physics. If neutralinos are real, they wouldn't just solve the dark matter riddle, they'd crack open supersymmetry's treasure chest, revealing a universe teeming with particles and fields we've never imagined. It would mean nature loves symmetry so much it doubled the cosmic cast without telling us, and if they're not found, that absence would force a reckoning, a pivot toward even stranger possibilities like dark matter, not as particles at all, but as folds in space-time itself. The neutralino story is still being written in the hum of particle accelerators and the silence of underground detectors. Whether it's confirmed or not, its ghostly presence challenges us to ask, how many layers of reality are still out there waiting to step into the light? Gravity is the force we know best, the pull that keeps our feet on the ground and planets in their orbits, yet it's also the most mysterious. While we can describe its effects with stunning precision using Einstein's general relativity, the deeper question remains: what carries gravity at the smallest scales? Enter the graviton, the hypothetical particle that would make gravity a quantum field like electromagnetism or the strong nuclear force. Picture the universe as a vast network of invisible threads, each force woven from its own unique particle: photons for light, gluons for atomic nuclei. Gravitons would complete this tapestry, the unseen messengers of spacetime's curvature, flickering between masses to orchestrate the cosmic dance of attraction. But here's the catch: unlike other force-carrying particles, gravitons refuse to play nice with quantum mechanics. The math breaks down catastrophically when you try to squeeze gravity into the quantum framework, spitting out infinities no known trick can reconcile. It's like trying to write a symphony using only noise. The deeper you go, the more chaotic it becomes. This isn't just a technical hiccup, it's a chasm between the two most successful theories in physics, each flawless in its domain yet mutually incompatible. Unifying them isn't just a puzzle, it's the holy grail, a theory of quantum gravity that could rewrite our understanding of reality. The challenges are staggering. Gravitons, if they exist, will be unimaginably faint. A single proton might emit one graviton every 10 billion years. Detecting them directly would require a sensor so massive it'd dwarf Jupiter, just to catch a whisper from two colliding black holes. Yet indirect hints tantalize. The gravitational waves LIGO detected in 2015 align eerily with predictions assuming graviton-like excitations in spacetime. Even the holographic principle, with its vision of reality as information projected from a distant surface, suggests gravitons might not be particles at all, but emergent phenomena like waves on an ocean we've mistaken for objects. The stakes couldn't be higher. If gravitons exist, they'd unlock secrets from the Big Bang's first moments to the fate of black holes. String theory, loop quantum gravity, and other candidates for quantum gravity all predict them, but in wildly different forms. Some models suggest gravitons could leak into extra dimensions, explaining why gravity is so weak compared to other forces. Others propose they're entangled with dark matter, their hidden interactions shaping galactic structures. And if we ever harness them, the dream of anti-gravity or warp drives would inch from fantasy to physics. Yet skepticism lingers. Some argue gravity isn't a force to be quantized at all, but a geometric illusion. The way a movie screen's curve distorts images without any projector particles. Others see gravitons as placeholders for a deeper truth we haven't yet grasped. But whether they're real or not, the search itself is reshaping science. Every dead end forces us to ask harder questions, to peel back another layer of the universe's design. And somewhere in the quantum foam or the fabric of space-time, the answer might be waiting, not as a particle, not as a wave, but as a key to the cosmos' grandest secret. Einstein envisioned time as a river, smooth, continuous, flowing unbroken from past to future. But what if that river is actually a series of tiny droplets? That's the radical idea behind the chronon field, a hidden layer of reality where time isn't a seamless fabric but stutters forward in discrete, indivisible chunks. These hypothetical packets, called chronons, would be the smallest possible units of time, like pixels in a cosmic movie, each frame advancing reality in minuscule jumps too small for any clock to measure. If true, it would mean our perception of time's flow is an illusion, a trick played by the mind stitching together a stop-motion universe. the math behind chronons isn't just speculative. Quantum mechanics already hints at discreteness in other fundamental quantities: energy, momentum, even space itself. Planck time, the interval it takes light to travel the shortest meaningful distance in physics, is roughly 10 to the minus 43 seconds. Could this be the chronon's duration? Some theories suggest that at this scale, time might tick like a metronome with the chronon field governing the rhythm. Picture a cosmic flipbook where reality updates trillions of times per second, each chronon marking a new snapshot of existence. This challenges relativity at its core. Einstein's spacetime is a flexible continuum warped by gravity but always smooth. Chronons would replace that with something granular, a universe where time has texture, like sandpaper beneath the equations. The implications are dizzying. Near a black hole's singularity, where gravity bends time to extremes, chronons might pile up or stretch thin, creating exotic effects like time crystals, structures that repeat not just in space but in time, like a snowflake with rhythms instead of symmetry. Even quantum weirdness could get an explanation. Particles behaving unpredictably might simply be hopping between chronons, their paths flickering like a glitching video. But how would we ever detect such a fleeting phenomenon? The answer might lie in the most accurate clocks ever built. Atomic clocks precise to within 1 second over billions of years could reveal chronons if time truly moves in steps. Imagine listening to a song on a record player. If the needle skips too subtly, the music still sounds smooth, but with enough precision, you'd catch the gaps. Similarly, if chronons exist, clocks might show tiny discrepancies, stutters in their ticks that betray time's hidden granularity. Experiments are already pushing these limits, with optical lattice clocks so sensitive they could spot deviations in the flow of time itself. The wildest possibility, chronons could rewrite causality. In a continuous universe, cause always precedes effect. But if time is pixelated, there might be moments where the next chronon isn't strictly determined. A quantum leap in time's structure that allows for microscopic violations of sequence. It wouldn't mean time travel, but it could blur the edges of what we consider now, suggesting reality's clockwork has more play in its gears than we thought. Whether chronons are real or not, the idea forces us to confront a profound question. Is time truly fundamental, or is it something that emerges from deeper physics? The chronon field hints at a universe where even time itself might be built from something smaller, something hidden, a cosmic code we're only beginning to decipher. What if dark energy isn't just one thing, but a cosmic shapeshifter blending phantom energy's destructive potential with quintessence's gentle push? That's the tantalizing premise behind the quantum field, a theoretical hybrid that could rewrite our understanding of cosmic acceleration. Unlike static dark energy models, this field wouldn't just nudge galaxies apart, it would oscillate between phases, sometimes acting like phantom energy, tearing spacetime apart, and other times fading into the background like a quiet cosmic tide. The result, a universe where dark energy's strength isn't fixed but pulses like a heartbeat across billions of years. Picture a pendulum swinging between two extremes. On one side, phantom energy's repulsive gravity grows stronger over time, dooming the cosmos to a catastrophic big rip. On the other, quintessence, a subtler field that weakens as space expands, like a spring slowly losing tension. The quantum field bridges these opposites, its behavior dictated by an internal tug of war. Early in cosmic history, quintessence-like properties might have dominated, gently steering galaxies apart. But as the universe grew colder and emptier, phantom energy could gain the upper hand, cranking expansion into overdrive. This duality solves a glaring puzzle: why some observations suggest dark energy's strength has changed over time while others insist it's constant. The clues lie in the cosmos architecture. Surveys mapping millions of galaxies reveal subtle inconsistencies in how structures cluster at different epochs, hinting that dark energy's influence might have wobbled. The quantum field's oscillations would imprint these irregularities like waves lapping at different shores. Even more compelling are Type Ia supernova, the standard candles that first revealed cosmic acceleration. Recent studies of these exploding stars suggest dark energy's equation of state, the key to its behavior, might not be a fixed number but a variable one, drifting toward phantom-like values as the universe ages. But the theory's real brilliance lies in its escape clauses. Pure phantom energy leads to an inevitable big rip, while quintessence often fizzles out too soon to match observations. The quantum field dodges both fates by self-regulating. When phantom-like effects grow too strong, the field's quintessence component reasserts itself, like a thermostat kicking in to prevent overheating. This dance could stretch indefinitely, delaying cosmic doomsday or even avoiding it entirely. Some models suggest the oscillations might eventually dampen, leaving the universe in a quiet, eternal expansion, a far gentler fate than phantom energy's shredding of space-time. The implications ripple beyond cosmology. If the quantum field exists, it might interact with other hidden fields like the Higgs or inflaton, weaving a complex web of influences we've barely begun to trace. Particle colliders probing extreme energies could uncover echoes of these interactions, while next-generation telescopes like the Vera Rubin Observatory might catch the field mid-oscillation, its fingerprints etched in the distribution of galaxy clusters. Yet mysteries remain. Why would such a field emerge in the first place? Is it fundamental or a side effect of deeper physics? And if it's oscillating now, could it have done so in the past, perhaps triggering inflation's explosive birth? The quantum field doesn't just challenge what we know about dark energy. It forces us to ask whether the cosmos has rhythms we've yet to hear, a hidden cadence beneath the expansion we measure. And that's a question worth listening for. Imagine a universe where particles don't follow the usual rules, where matter isn't confined to tidy whole number dimensions but fragments into something stranger. That's the essence of unparticles, a theoretical concept so bizarre, it redefines what we consider real. Unlike electrons or quarks, which behave predictably under the standard model, unparticles exist in fractional dimensions, blurring the line between particle and wave, between something and nothing. Picture sand slipping through your fingers. It's neither fully solid nor fully fluid, but something in between. Unparticles are like that sand, defying conventional physics by operating in a mathematical twilight where traditional laws break down. The unparticle field, if real, wouldn't just add another force to the universe, it would rewrite the playbook entirely. Normally, particles have distinct masses and spins, but unparticles scale differently, behaving like a fog of possibilities rather than discrete objects. This fog could permeate space as a hidden field, interacting so weakly with known matter that it's effectively invisible. Yet its influence might still be detectable through subtle anomalies, tiny deviations in particle collisions, unexplained energy losses in high-energy experiments, or even distortions in the cosmic microwave background. It's like feeling a draft in a sealed room. You can't see the source, but you know something's there. What makes this field truly revolutionary is its potential to bridge gaps in physics. Dark matter's gravitational effects, for instance, could arise from unparticles clumping in ways normal matter can't. Their fractional dimensions might allow them to weave through space-time differently, creating the invisible scaffolding that holds galaxies together. Even black holes could harbor unparticle activity near their singularities, where extreme gravity twists the rules of reality. Some theories suggest unparticles might mediate forces beyond the standard model, acting as cosmic middlemen for interactions we've never imagined, like a secret language spoken only at the universe's most fundamental level. The hunt for unparticles is already pushing experimental physics to its limits. Particle colliders like the Large Hadron Collider are probing unprecedented energy ranges, searching for collisions that spit out not just new particles, but energy patterns that don't fit any known equations. Other experiments track neutron decay with ultra-sensitive detectors, watching for missing energy that could hint at unparticles carrying it away. And in deep space, telescopes scan for anomalous gamma-ray signatures that might betray the field's presence. Yet the boldest idea isn't just about detection, it's about reimagining reality. If unparticles exist, they'd force us to accept that the universe isn't just built from Lego-like blocks, but from ethereal fragments that resist definition. They'd challenge the very notion of dimension, suggesting that the fabric of existence might be frayed at the edges, with threads we're only beginning to tug. Whether they're real or not, unparticles remind us that the cosmos still holds mysteries wilder than fiction, and that the next great discovery might not fit any mold we've prepared. The universe loves symmetry, not just in snowflakes or spiderwebs, but in its deepest laws. Electromagnetism's elegant equations mirror gravity's curvature, while quantum particles pair up like dancers in an endless cosmic ballet. But here's the unsettling truth: these symmetries are broken. The forces we see today, gravity, electromagnetism, the strong and weak nuclear forces, are nothing like their primordial ancestor, a single, unified superforce that ruled the universe's first trillionth of a second. So what happened? Hidden beneath the chaos might lie the symmetry field, a primordial architect that once locked all forces into perfect harmony before shattering them into the fragments we recognize today. Picture a frozen lake at absolute zero, its surface flawlessly smooth. That's the symmetry field in its pristine state, a perfect balance where all forces are identical, indistinguishable. But as the universe cooled, cracks formed. Like ice thawing into jagged flows, the field's symmetry spontaneously broke, splintering the superforce into the four distinct interactions we now observe. This isn't just poetic analogy. The Higgs field, which gives particles mass, is a modern echo of this process, a relic of symmetry breaking frozen into the cosmos fabric. The symmetry field would have operated at far higher energies, its fractures setting the stage for everything from atomic bonds to the expansion of space itself. The evidence hides in particle physics quirks. At extreme energies like those inside the Large Hadron Collider, electromagnetism and the weak nuclear force begin to act alike, a glimpse of their original unity. Theorists argue this is no accident, but a shadow of the symmetry field's influence, its remnants still whispering through quantum equations. Even the mysterious hierarchy problem, why gravity is so weak compared to other forces, might trace back to how this field fractured. Imagine a pane of glass shattering. Some pieces fly far, others stay close. Similarly, the symmetry field's breakup could have left gravity diluted across hidden dimensions, while nuclear forces remain tightly bound to our familiar four. But the most tantalizing clue lies in magnetic monopoles. These hypothetical particles, long hunted as evidence of grand unification, would be cosmic fossils of the symmetry field's reign. If discovered, they'd confirm that the forces were once one, and that this primordial field orchestrated their divorce. Until then, we're left with mathematical hints, subtle patterns in particle collisions, asymmetries in the cosmic microwave background, even the puzzling lightness of the Higgs boson. Each could be a breadcrumb leading back to the symmetry field's fingerprints. What's breathtaking is how much rides on this idea. If the symmetry field exists, it didn't just shape forces, it set the rules for reality's unfolding. Its breaking determined the constants of nature, the stability of atoms, even the universe's lifespan. Tweak its parameters slightly, and stars might never have ignited. In this light, the field isn't just a historical artifact. It's the silent composer of the cosmic symphony, its early decisions echoing across billions of years. And somewhere, in the debris of particle collisions or the whispers of ancient light, its final secrets might still be waiting. At scales smaller than an atom, space-time itself begins to fray, not into smooth emptiness, but into a seething quantum foam where particles wink in and out of existence so rapidly, they defy all classical notions of reality. This isn't just microscopic chaos, it's the domain of the Planck field, a hidden layer of physics so fundamental, it might be the brushstroke that paints existence itself. Named after Max Planck, the father of quantum theory, this field isn't just another player in the cosmic game. It's the canvas the game is played on, governing the shortest possible distances and the briefest measurable moments in the universe. Picture the universe's fabric under a microscope, zoomed in until time and space dissolve into a froth of virtual particles and fluctuating energies. At this level, spacetime isn't smooth or continuous, it's granular, like the pixels on a screen. The Planck length, about 10 to the minus 35 meters, marks the smallest meaningful division of space, while Planck time, the interval it takes light to cross that distance, is the universe's ultimate stopwatch. Within this realm, the Planck field churns, orchestrating the quantum foam's chaos. It's here that particles borrow energy to flicker into being, where black holes evaporate into Hawking radiation, and where the seeds of quantum gravity might finally sprout. What makes this field so radical is its role in stitching together relativity and quantum mechanics. Einstein's gravity describes spacetime as a smooth, bendable sheet, while quantum physics insists everything is discrete and jumpy. The Planck field could be the missing translator, a hidden mediator that reconciles these clashing worldviews. Some theories suggest it generates spacetime's very structure, like a loom weaving the threads of reality. Others propose it's the source of dark energy, its fluctuations stretching the cosmos apart. Even the Big Bang might trace back to this field's instability, a quantum hiccup that ballooned into everything we know. The implications ripple outward. If the Planck field exists, it could explain why gravity is so weak compared to other forces. Imagine gravity's strength leaking into extra dimensions through this field's quantum foam, diluting its influence in our observable universe. Or consider black holes where space-time curvature becomes infinite at the singularity. The Planck field might prevent this breakdown, imposing a smallest possible scale where quantum effects smooth out the math's infinities. It's like cosmic safety net, ensuring reality never tears completely. Yet detecting this field is a staggering challenge. Probing the Planck scale would require energies a quadrillion times beyond what the Large Hadron Collider can muster, an impossibility with current technology. But indirect hints tantalize. Quantum fluctuations in empty space, the Casimir effect's phantom forces, even anomalies in gravitational wave data. Any of these could be echoes of the Planck field's whispers. Some physicists argue that spacetime's pixelation might subtly alter high-energy particle collisions or leave faint imprints in cosmic microwave background patterns. The boldest idea that the Planck field isn't just physics' foundation but its frontier. If we could decode its language, we might unlock time travel's math, harness zero-point energy, or even glimpse the universe before the Big Bang. For now, it remains a ghost in the equations, a reminder that reality's deepest layers are still wild, untamed, and waiting to be discovered. Consciousness is the one puzzle science struggles to explain. We can map neural networks, decode neurotransmitters, yet still can't pinpoint how electrical impulses become subjective experience, that vivid inner world of thoughts and sensations we all inhabit. But what if awareness wasn't confined to brains at all? What if it's woven into the fabric of reality like gravity or electromagnetism, a fundamental field waiting to be discovered? This is the essence of the consciousness field theory, a daring fusion of panpsychism, the ancient idea that mind permeates everything, and cutting-edge quantum physics. Imagine dropping dye into a river. The color spreads, blending with the water until they're indistinguishable. The consciousness field operates similarly, according to proponents, permeating all matter as an intrinsic property of the universe. In this view, electrons don't just have charge and mass, they possess a rudimentary form of awareness, infinitesimal but real. When these particles organize into complex structures like brains, that latent consciousness amplifies like countless whispers merging into a voice. It's not that your brain generates consciousness, it tunes into it the way a radio picks up invisible broadcasts. Quantum mechanics adds tantalizing weight to this idea. Experiments like the double-slit test show particles behave differently when observed, as if they're somehow aware of being measured. Traditional interpretations call this wave function collapse, but consciousness field theorists propose a bolder explanation. The act of observation resonates through this hidden field, influencing the system. Picture ripples in a pond disturbing floating leaves. The observer's consciousness could ripple through the field, nudging particles into definite states. This isn't magic, it's physics operating on scales we've yet to quantify. The implications ripple beyond theory. Near-death experiences where people report lucid awareness during clinical brain death might reflect consciousness persisting outside neural activity, like a radio playing briefly after unplugging. Even plant intelligence studies take on new light. The famed Mimosa pudica, which learns to stop reacting to harmless stimuli, could be tapping into this field's rudimentary cognition. The field wouldn't just explain human experience, it'd redefine life itself as nested layers of a universal mind. Skeptics, of course, demand empirical proof. How do you measure something as nebulous as a consciousness field? Experiments in integrated information theory, which quantifies consciousness as a property of interconnected systems, hint at a path forward. Researchers are designing protocols to detect anomalies in quantum systems when influenced by focused human intention, seeking deviations that might betray the field's presence. Other teams study brainwaves in meditators, searching for patterns that synchronize across distances without physical interaction, as if minds are antennas picking up the same cosmic signal. Yet the boldest idea isn't about validation, it's about unification. If the consciousness field exists, it could bridge the gap between science and spirituality, between the measurable and the felt. The mystic's oneness and the physicist's equations might describe the same reality, one from the inside, the other from the outside. Whether this theory is proven or not, it forces us to confront a humbling possibility, that the universe isn't just aware of itself through us, but that awareness might be its most fundamental feature waiting to be decoded. Imagine our universe as a single soap bubble floating in an infinite cosmic froth. Each neighboring bubble a self-contained reality with its own laws of physics, its own versions of stars and planets, even its own alternate versions of you. This is the multiverse, and if it exists, there might be a hidden force stitching these parallel worlds together, the multiverse field. Unlike any known force, this meta-field wouldn't just govern particles or space-time. It would weave through the boundaries between universes, a cosmic loom connecting every possible variation of reality. And the most mind-bending part, we might already have evidence of its fingerprints in the oldest light in existence, the cosmic microwave background. The idea hinges on collisions. If our universe once bumped against another in the foam of the multiverse, the energy from that impact could have left scars in the pattern of the cosmic microwave background. Picture two soap bubbles gently touching the spot where they meet would ripple, distorting their surfaces. If something similar happened between universes, it could explain the so-called cold spot detected in the microwave background, a vast region of space unusually devoid of radiation. Some theorists argue this anomaly is too large and too cold to fit standard cosmic models, but a collision with a neighboring universe through the multiverse field. That could do it. Then there's the question of quantum entanglement. Particles in our universe can become mysteriously linked across vast distances, reacting instantly to changes in their partners. What if this spooky action isn't confined to our cosmos? The multiverse field might allow particles to entangle across realities, creating quantum bridges between worlds. Think of it as a cosmic Wi-Fi network where data packets, or even entire quantum states, could hop between universes along hidden channels in the field. It's not teleportation, but something stranger, a fundamental connectedness written into the fabric of existence itself. But how would such a field even work? One theory suggests it operates like a higher dimensional symphony, with each universe vibrating at a unique frequency. The multiverse field would be the medium through which these vibrations interact, resonating in ways that could subtly influence the physics of neighboring realities. If true, it might explain why our universe's constants, the strength of gravity, the mass of electrons, are so finely tuned for life. Tiny variations in the field's vibrations could nudge other universes toward wildly different laws, while ours landed in the sweet spot by chance, or perhaps by some deeper, hidden logic. The hunt for proof is already underway. Telescopes like the Planck satellite have mapped the cosmic microwave background in unprecedented detail, searching for statistical anomalies that might betray contact with other universes. Meanwhile, quantum physicists are probing whether entanglement could leak beyond our spacetime, looking for particles that behave as if they're sensing invisible partners in parallel worlds. And if we ever detect gravity waves from the Big Bang with unusual signatures, they might carry echoes of the multiverse field structure imprinted in the first moments of creation. Whether the multiverse field is real or not, it forces us to confront a breathtaking possibility that everything we know might be just one verse in an infinite cosmic poem, each line written in the subtle language of hidden connections. And somewhere in the static of the microwave background, or the flicker of a quantum experiment, the next stanza might already be whispering to us. From the Higgs field's invisible grip giving particles mass to the phantom energy threatening to rip spacetime apart, these hidden forces aren't just science fiction, they're the wildest frontiers of reality itself. We've explored galaxies sculpted by axion fields, universes bubbling from quantum foam, even the chilling possibility that consciousness itself might be woven into the fabric of existence. Each theory is a puzzle piece in a cosmic mosaic we're only beginning to assemble. Think about it. Dark energy might not just be pushing galaxies apart, but evolving, its strength ebbing and flowing through a quantum field's mysterious oscillations. The gravitational waves we detect could carry echoes of tensor fields warping dimensions we can't even see. And somewhere out there, magnetic monopoles, lonely north poles without their southern twins, might hold the key to unifying all of nature's forces. These aren't just ideas, they're potential revolutions waiting to rewrite physics textbooks. But here's what truly boggles the mind. If even one of these fields is real, the implications are staggering. Discovering the inflaton field could reveal how our universe burst into being, while cracking the code of the Planck field might expose the pixelated underpinnings of spacetime itself. The multiverse field could prove we're just one page in an infinite cosmic library, and the Akashic field might mean every thought, every event, is forever imprinted on reality like grooves in a record. So which theory resonates with you? Do you think dark matter is made of ghostly actions, or does the morphic field's living universe feel closer to the truth? Maybe you're convinced that torsion fields are twisting galaxies into strange alignments, or that zero-point energy hides the ultimate power source. Drop your favorite in the comments, let's geek out over the possibilities. And if you're hungry for more mind-bending mysteries, hit subscribe. The universe has plenty of secrets left to spill, and we're just getting